Hi everyone, welcome back to Astrophobic. In today's video, we're diving into the mysterious world of antimatter and exploring how it differs from regular matter. First, let's quickly recap what regular matter is. So, what exactly is matter? Simply put, matter is anything that has mass and takes up space. This means everything around us, from the air we breathe to the food we eat, is made of matter. Matter is made up of tiny particles called atoms. Atoms are like the building blocks of everything in the universe. Each atom has three main parts: protons, neutrons, and electrons. Imagine an atom like a miniature solar system. At the center you have the nucleus, which contains protons and neutrons. Protons have a positive charge and neutrons have no charge. Surrounding the nucleus, you have electrons, which have a negative charge. They move around the nucleus in regions called electron clouds. These parts work together to form atoms, which then combine to make up all the different materials and objects we see in our daily lives. The concept of antimatter was first proposed by physicist Paul Dirac in 1928. Back in 1928, a physicist named Paul Dirac came up with a pretty interesting idea. He was working on some complex math equations and noticed something surprising. These equations suggested that for every particle, like an electron, there could be another particle with the same mass, but an opposite charge. This was a big deal, because it meant there could be a whole set of mirror particles out there, which we now call antimatter. Dirac's equation was revolutionary because it predicted the existence of these particles before anyone had actually seen them. Think of it like finding a clue in a mystery story that hints at something amazing yet to be discovered. This idea set the stage for future scientists to start looking for these mysterious particles in the real world. In 1932, Carl Anderson discovered the positron, the antimatter counterpart of the electron. Fast forward to 1932, and a scientist named Carl Anderson was working with cosmic rays, tiny particles that come from outer space. While examining tracks left by these particles in a cloud chamber, Anderson discovered something incredible: a particle that behaved like an electron but had a positive charge. He named this particle the positron. This was the first time antimatter was observed in the real world, proving Dirac's theory right. Imagine the excitement of that moment. Anderson's discovery was like finding the missing piece of a puzzle. It confirmed that antimatter wasn't just a theoretical idea, but something that existed. This breakthrough earned Anderson a Nobel Prize and opened a whole new field of study in physics. So what exactly is antimatter? Antimatter is composed of antiparticles, which are mirror images of regular particles, but with opposite charges. Antimatter is pretty much the opposite of regular matter. For every particle that makes up matter, like electrons and protons, there is a corresponding antiparticle in antimatter. These antiparticles are similar to their counterparts in almost every way, but have opposite charges. For example, a positron is like an electron, but has a positive charge instead of a negative one. Similarly, an antiproton is like a proton, but has a negative charge. Properties. One of the key properties of antimatter is that its particles have the same mass as their matter counterparts, but with opposite charges. This means a positron weighs the same as an electron, but is positively charged. An antiproton weighs the same as a proton, but is negatively charged. Another interesting property of antimatter is what happens when it meets matter. When a particle and its corresponding antiparticle come into contact, they annihilate each other. This means they destroy each other completely, releasing a lot of energy in the process. This annihilation process is why antimatter is so fascinating and why it's a popular topic in both science fiction and real-world physics. So, what sets matter and antimatter apart? The biggest difference is their charge. Particles in regular matter have a specific charge, like electrons, which are negatively charged, and protons, which are positively charged. In antimatter, these charges are flipped. For example, positrons have a positive charge, and antiprotons have a negative charge. When matter and antimatter come into contact, something incredible happens. They annihilate each other. This means they destroy each other completely and release a huge amount of energy. This annihilation process is why we don't see much antimatter around us. If it were here, it would quickly disappear when it meets matter. One of the biggest mysteries in physics is why the universe is made mostly of matter, even though the Big Bang should have created equal amounts of both. Now here's something that really puzzles scientists. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. But when we look around, we see that the universe is almost entirely made of matter. So, where did all the antimatter go? This question is one of the biggest mysteries in physics. Scientists have come up with several theories to explain this. Some think there might be slight differences in the way matter and antimatter behave that cause matter to become more dominant. Others are exploring the idea that there might be regions of the universe where antimatter is more common. Research is ongoing, and every new discovery helps us get a little closer to solving this cosmic mystery. By studying these differences and trying to understand why matter won out over antimatter, scientists hope to uncover more about the origins and fundamental laws of our universe. Antimatter might sound like science fiction, but it has real-world applications. You might think antimatter is just something out of a sci-fi movie, but it has practical uses right here on Earth. One of the most important uses of antimatter is in medicine. PET scans, which doctors use to look inside the body and diagnose diseases, rely on positrons, the antimatter counterpart of electrons. These scans help doctors detect things like cancer and brain disorders, making them a vital tool in modern healthcare. Looking to the future, scientists are exploring the idea of using antimatter for energy production and even space travel. When matter and antimatter annihilate each other, they release a huge amount of energy. If we could harness this energy, it could provide a powerful source of fuel. This concept is still theoretical, but it holds exciting potential for advancements in technology and exploration. Studying antimatter helps scientists understand fundamental symmetries in nature and the origins of the universe. Antimatter is not just about cool technology, it's also crucial for understanding the universe. By studying antimatter, scientists can learn more about the fundamental symmetries in nature. These symmetries are like the basic rules that govern how everything in the universe behaves. Additionally, investigating antimatter helps scientists explore big questions about the origins of the universe. For instance, understanding why there is more matter than antimatter around us could reveal important insights about the early moments after the Big Bang. This research pushes the boundaries of what we know and helps us piece together the story of how everything came to be. In short, antimatter isn't just a fascinating concept. It's a key to unlocking some of the biggest mysteries in science and could lead to groundbreaking advances in technology and our understanding of the universe. To sum up, antimatter is a fascinating counterpart to regular matter, with opposite charges and unique interactions. Let's quickly recap what we've covered. Antimatter is made up of antiparticles, which are like mirror images of regular particles, but with opposite charges. We talked about how Paul Dirac's theory led to the discovery of the positron by Carl Anderson. We also discussed how antimatter and matter annihilate each other when they meet, releasing a lot of energy. This annihilation process has practical uses in medicine, like PET scans, and could potentially be used for energy production and space travel. Studying antimatter helps scientists understand the universe's fundamental rules and the origins of matter.